Hi, this is Professor Stucard, and in this video we're going to discuss linear regression. So our goals for this lecture, we want to understand how to create linear models in R based upon data. Then we're going to talk about how we can create functions to actually make our predictions based on our models. And then also, again, we're going to talk about the limitations of creating any predictive model, although in this case, again, we're focusing on just linear models or lines as our functions. So, for the example, we're going to use our Gapminder dataset, and I want to filter only for the results for the United States. And then what I want to look at is I want to look at how the year, right, and life expectancy are related to each other. Now, year is going to be along my horizontal, that's my x-axis. And again, typically whenever we're doing something that involves a measure of time, we make that on our x-axis, which means that's our explanatory variable. And then again, life expectancy then becomes my y variable or my response variable. So again, here's my code, Gapminder. I'm piping it into, well, first of all, the filter function so that I can filter just for the United States. Then I'll pipe those results into ggplot so I can create my scatter plot. With again, year along the x, life expectancy along the y, and I want a scatter plot, which means I'm adding the layer for a geom point. All right. Here is the data. I take a look, and just by inspecting this visually, yes, it looks like there's definitely a pattern to this data, and it looks like those dots pretty much fall on a straight line. So we can add this potential pattern to our scatter plot of data by just adding another layer to ggplot. The layer we're going to add is the GeomSmooth function. Now, if you want a linear model, we have to set that argument inside of GeomSmooth. So again, there's different types of regression models we can use. Again, we're going to start with just the simplest ones, which are linear models. And so in the R programming language, LM always stands for linear model. And so again, inside the GeomSmooth function, we're going to set method. Method is the argument, and we're going to set that argument as LM for a linear model. So in my code, this is what it looks like. Again, I'm keeping the exact same code from before. I'm just adding another layer for GeomSmooth, and I add that GeomSmooth layer with the method being that I want a linear model, and boom, there we go. We have this line. Now there is a line that basically describes where those points are fairly well. And of course, it's not perfect, right? Obviously, there's several points that are off of that line. But again, it's doing a pretty good job of modeling what's going on. Now, if you notice, there is that gray bar that is around my blue line. So the blue line, the blue is my regression line. The gray bar around it has to deal with the uncertainty. All right. So again, it's modeling real world data. It's not going to be perfect. There's always going to be some uncertainty inherent in our models, in our predictive functions. There's always uncertainty, and that is represented again by that gray band. Now, the wider that gray band is, the more uncertain we are about the model. The smaller the gray band, the more we can be confident that it is accurately describing what's going on. If you want to remove that gray band, we set the argument SE equal to false. So again, if I take that same code and I now just add that extra argument at the end. So again, the Gapminder, I filtered it. I was doing a ggplot, year, life expectancy, scatter plot, GeomSmooth. Again, I want a linear model, and I just set my SE equal to false. And now again, that gray band will be gone, and I just have the blue line, which is again typically how we I guess draw our visualizations. Now, GeomSmooth, there's other arguments you can actually use with it as well. So sometimes, again, if your scatter plot does not necessarily take up the entire plot screen, it's not going to draw a regression line for points that don't really exist, but you can still extend it by setting the argument full range equals to true. And then again, you can customize it in a bunch of other ways with color and line type and size. Because again, you can basically customize almost any aspect of any visualization in the R programming language. If I want to create models based on the data, we're going to be using the Tidy Models package. All right. Now, tidy models is similar to tidyverse as it's actually several packages in one. And so we can load a bunch of different packages all kind of at the same time. And again, we would do the same with any other package. Install that package as tidy models in quotes, then library tidy models so that we can access the functions involved. And there's actually some crossover with tidy models and tidyverse. They actually have some of the same packages as well. Because again, it's when we say the tidy universe, it's really a universe of different packages. Okay, now how can I use the tidy models packages based on my data? So we're going to start with, again, just linear regressions and come up with linear regression lines. So the first step in my code would be, well, to specify the model. And again, I want a linear regression model. Then I need to pipe that into the set engine function. So again, we're using the tidyverse kind of scheme where we keep piping. So we're going to pipe that into the set engine function. And I need to set function as LM, again, right? That linear model, right? LM. It's always LM for the programming language R. And then we're going to pipe that into the fit function. All right. So again, I want a linear regression using the linear model engine. And then I want to create a best fit based upon my variables, which is my response variable first, then the tilde, then my explanatory. All right, so again, we're talking about mathematical equations. Again, typically the R programming languages use that little tilde instead of the equal sign, since obviously the equals is a comparison operator. And then again, our response variable is our Y variable, our explanatory is our X variable. So again, whenever we set this up, those are the parts that we'd actually be replacing, would be in this last line. Then also, the last argument is our data set, and we don't want to say data equals. And so this is the way that a lot of the older R functions worked pre-tidyverse. And so again, when you use some older functions like, say, the fit function, which has existed for a very long time, the last argument is actually your data argument. So at the very, very end, you would say data equals, and then you would actually specify what your data set is. So again, that is the main code that you want to keep in mind when using the tidy models linear regression functions. Okay, so let's actually use that for our example. Now, I'm actually going to create my own data set with just the observations for the United States. I know I used the filter before, but let's actually set this up as its own data frame called America. So I'm creating a data frame called America, which comes from the original data frame Gapminder, which we filtered by the country being the United States. And now again, I'm using my linear regression. I'm piping that into the set engine, which is LM. I'm piping that into fit. And I have life expectancy as my response variable, the tilde, and then year as my explanatory variable. And then of course my data equals my data set America that I just specified. All right, so when I run that code, my output now says coefficients, intercept, and year. Now the way we're going to interpret this, well, the intercept is the intercept. That other value is my slope, or my rate of change. And the way we interpret this is that for every one increase, or every increase in 1 unit for the variable year, my response variable is going to increase by that value, so the 0.01888. So again, that's my slope. For every one unit increase in year, life expectancy is going to increase by 0.1888. So again, that's the way we're going to interpret that. Now, if you want to create more outputs and get a little bit more data about your model, we can actually pipe this into the tidy function, and it's going to create a tibble for us. So again, all the same exact code that I had before, linear regression piped into the set engine for a linear model, piped into my fit for life expectancy as my response, year is my explanatory from the dataset America, and if I pipe it into tidy, my output now is a data frame, or a tibble that is 2 by 5. It includes a few more, numerical results for us as well. We still have, right there in yellow, the two important values that will let us create our linear model. We have our intercept is negative 300 Remember, the other one was negative 300.4, I think it was. And then our slope is 0.189. Now they rounded it one more decimal place for us. And again, that's still how we can create our linear model. That still describes what's going on with our data. But the nice part is, you see that next column over is our standard error. And so our standard error has to do with the margin of error and goes back to the uncertainty that that exists within our model, and how certain and uncertain we should be about certain things. Okay, we're going to leave that alone for now because, again, we're just going to work on creating our linear model. So we're going to take that, we can take that data and we can actually plot our own lines using the GeomAB Line function. So again, we would add this as a layer to ggplot, and you directly define the y-intercept and the slope. And then, as you can see, you can also define a bunch of the other arguments as well, like line type, color, size, all that other stuff. But if I go back, and again, I'm looking at just the data from America, I'm piping that into ggplot, again, year along the x, life expectancy along the y, it's a scatter plot. I can actually set up my own regression line as just doing GeomAB line, add that layer with my intercept equal to negative 300.4 and slope equal to 0.189, and boom. Now we have a line that we actually created ourselves that is superimposed over our data. And again, if I wanted to change colors, I could, or thickness, or make it dashed. I could set all those arguments however I would like. Now, the important part. How do I make predictions? Now that I know the slope and the intercept, I want to make predictions about life expectancy. Well, we can create a linear function now based on the data using that mx plus b form, right? Y equals mx plus b, or f of x equals mx plus b. Now, we know that the slope was the 0.189. The y-intercept was negative 300.4. So, yeah, there we go. We plug that right in. So f of x equals 0.189x minus 300.4. Now I can use this linear model to predict my life expectancy. So let's say I want to predict what life expectancy was in 1977. All right. Well, that means x, right? X being my explanatory variable for year. I'm going to let that equal 1977. And when I plug that in, well, then it's just order of operations on that right-hand side. So multiply first 0.189 times 1977, then subtract 300.4, and I end up with the result 73.253. So again, I came up with a linear model. I plugged in the year 1977, and my model predicts that the life expectancy should be 73.253. So again, that's the prediction. Now, my model predicted a life expectancy of 73.253. The given life expectancy from the data was 73. Now, all of the years for life expectancy are actually rounded to integer numbers, even though it's stored as a double. So again, that is the nearest integer value, which means, yeah, this worked really well. My model was really good at predicting life expectancy for 1977. My residual was very small. My guess was very close to what the actual value was. Okay, that's really nice. How do I create an actual function in R to do this so I can check a bunch of different data points? Okay, so first we need to create a function. So I'm going to call my function find life expectancy. All right, so I'm going to create a function called find life expectancy, which means I'm going to store that. I'm going to use my function. My one input is year, right? That's my only input, so I only need one input when I set up my function. And then my code is just going to be the 0.189 times x minus 300.4. So again, we can see this is really, really similar to our f of x function notation, right? Our function of x, f of x, and then, well, then the mathematical statement that we have down there. One thing you want to be really careful about when you're doing any sort of programming is that you must include the time sign. Almost all programming languages by default, if they see those two things next to each other, if you just said 0.189x, it's not going to see that as multiplication like we would normally do in mathematics. It's going to see that as its own type of variable. All right, so you have to include that times sign when you're doing programming. But now that I have created my function called find life expectancy, I can plug in 1977 and it's going to output exactly that same value, 73.253. So again, I have now created a linear model to predict life expectancy given the year. All right, so I've now created my first predictive model based upon my data set. Okay, so what does my model predict for life expectancy in 1620, right? So when the Pilgrims landed in Massachusetts, what is my life expectancy in 1620? Okay, run my function, and I'm going to plug in the year 1620, and I get a result of 5.78. So the average life expectancy was less than 6 years old. So, wait, does that make sense? Would we expect people to only live to be less than 6 years old? No, that doesn't make sense, because there's a limitation on this. All right, there's clearly a limitation on my model, and that's true for any model when it comes to predictions. And again, if I went further back and said, okay, well, what was the average life expectancy in 1450 before Columbus sailed to the Americas? You get a negative number. And if you say, well, and you check a bunch of other values, you can see that it doesn't always make sense. There's only a limited range that our prediction model is going to work. And we need to be aware of that. And again, that's going to be true of any model that we create. Any prediction model is going to probably predict some things well and other things poorly. And it just depends on how well we can fit to that given data. And again, being cognizant that, well, no matter how good our model is, there's going to be some times when it's just not that good. All right, so that wraps up for this video. So first of all, what represents linear model in R? Okay, pretty straightforward, right? Anytime you want a linear model in R, you're using the two letters. Okay, yeah. Second question, how do you add a trend line to your data visualization? All right, how do I add my best fit line? And then lastly, what package do we want to use to create our numerical models? And then how do I create those numerical models? And go through that code as well, right? Again, there's a bunch of piping features. Make sure you write that down, take some notes, figure out how you can find that information based upon your data. That is an important feature. And so make sure you've taken a note of that as well. All right, that wraps it up for this video. And as always, take care of yourselves.